This next section we're going to get into is going to be a little bit different. So we're actually going to make a connection between complex numbers and then trigonometry. So we're going to see how we can actually work with the two in correspondence with each other, and then how we can simplify some of our multiplication and division process with complex numbers. So we're going to start just by refreshing on what the complex plane is. So it still looks like our normal xy axis. The difference is our x-axis is considered our real axis, and then the y-axis is the imaginary axis. Okay. So every single number you plot, say I pick my real value to be 2 and my imaginary number to be -3, I would go ahead and plot this point, and it would represent +2 for the real component and -3 for the imaginary component. So remember, I stands for imaginary. So it gives us a way to connect to that origin. And just as a refresher, if you don't remember what I is, it helps us when we're taking square roots of negative numbers. So I is defined as the square root of -1, and I squared is equal to -1. So it's the only way we can take something, multiply it by itself, and result in a negative. So the nice thing about this is every single complex number we have in this complex plane is really defined by a vector, okay? So each complex number, which is given by x plus yi, is determined by a position vector. Which we'll call v, which is x, y, okay? So with that, we're going to be able to have the same kind of connection we do with vectors. So every single vector that I plot has an endpoint, which is x plus yi. So we can drop a triangle in here, a right triangle. This is our x component, this is our y component, and then that length out to that distance is exactly our magnitude of the vector. But you can also associate it to polar. It is that distance out there, okay? So we're able to have this connection with polar as well. We have some angle that this complex number forms with some distance. So we really can utilize this triangle in all of our trig relationships to come up with different ways to talk about the components of this. So if I look at cosine of theta, it's adjacent over hypotenuse. So in the same way that we are able to find the horizontal component for a vector, the x-coordinate can be given by r cosine of theta. And the y component can be given by r sine of theta. Okay, so this is going to be really helpful when we have to rewrite a complex number in trig form, and so on. The other relationships that we have are, this is a right triangle, so if I take x squared plus y squared, it's equal to the hypotenuse squared. And then also, if I'm given the xy coordinates and I need to come up with that trig form for it, well, this is going to be how I can utilize to find r. And I also need to figure out what theta is. So it's likely going to be some point on the unit circle. So you'd hopefully be able to recognize by figuring out what sine and cosine are. The other way you can do that is you can look at tangent of theta, and that's equal to the opposite over the adjacent. So this will deal with the sine of the value, and this will deal with the cosine of the value. You would just have to divide by r. So every single complex number can be written in terms of a radius and then an angle here as well. So since we have this, we're able to write our complex number in trig form or trigonometry form. So the idea is we have this complex number, x plus yi. Our x is r cosine of theta. Our y is r sine theta. And then we have I attached to it, okay? So something we can do, both of these have r involved, and then we're left with cosine of theta plus I times sine of theta. So we have a simpler way to rewrite this expression because really the only thing that matters is that theta value. The I is attached to sine. So the condensed form for writing this is we say r cis theta to stand for cosine, imaginary number, sine of theta. Okay. So in this case, remember, we do have a lot of ways that we can represent the same point on the unit circle. So we like to keep this nice where our R value is going to be positive. Or equal to 0. And we're just going to go once around that unit circle. Okay. So let's go ahead and let's try this out. Let's write this number in complex form. So we've got 8 cis of 3 pi over 2. Okay. So all that means is we have 8. The cis stands for cosine of that angle plus I sine of that angle. So again, knowing your unit circle, going to be important. And again, that 8 really just distributes out to everything. So this is 8 cosine of 3 pi over 2 plus 8I sine of 3 pi over 2. And then if you think about where 3 pi over 2 is, it is that bottom part of the y-axis. So really, cosine of that is going to be 0. And then sine of that is -1. So this complex number really has no real part. It just has an imaginary part, which is -8i. So it really is going to be plotted just on that y-axis. Okay. Let's try now to do the opposite. Given the complex number, let's write it in trig form. So I'm going to need to find two things. I'm going to need to figure out what is my R value and then also what angle this forms with that positive x-axis. So let's go ahead and draw a little picture just to help us out. Because I do need to know what quadrant I'm in. So in this case, my x value is going to be -√3. And my y value is what's attached to I. It's +1. So this point's going to be somewhere in that second quadrant. Okay. If I do go ahead and draw a straight line down, this would be 1 and this would be -√3. So the very first thing I'm going to do is I'm going to figure out what is R. So if I take x squared and add y squared, it's going to equal r squared. My x value is -√3. My y value is +1. √3 squared will give us +3. 1 squared is 1. And so that gives us 4 is our r squared value. And again, I'm going to take a square root, but I'm just going to assume r is positive. So the hypotenuse of our triangle is 2. Okay. Now I can utilize this. Again, I can figure out both what sine of theta and cosine of theta are. But again, our theta value is going to be the one that is in quadrant 2. So if I do take tangent of this value, that's equal to y over x. Our y value is 1. Our x value is -√3. So the way I like to personally think about these is we know our r value is 2. So if I take the top and bottom and divide it by 2, I'm not changing anything. And remember, tangent is the same thing as sine over cosine. So I'm looking where sine of theta is equal to 1/2 and cosine of theta is -√3 over 2. For the angle that happens with, that's a 30-degree angle. That's when sine of theta is 1/2 and cosine is that √3 over 2. And this angle is in quadrant 2. So my theta value has to be 5 pi over 6. Okay. So I have my angle, I have my value of r. So if I want to write this in our trig form, this would be 2 cosine of that angle plus 2I sine of the angle. Or condensed, our r value is 2. We have that cis to represent cosine, imaginary number sine, and the angle is 5 pi over 6. So this is that number in trig form, okay? So again, it's going to utilize your unit circle a lot. You're going to have to be able to figure out what each of these components are. We will work sometimes as well in degrees, but you do need to be very comfortable with your radians as well, okay? What I want to do now is I want to kind of talk about, we have multiplied complex numbers before in prior classes. We've divided complex numbers, and they're quite tedious to do because you kind of have to distribute things out. And we also talked about powers in some sense, but we're going to kind of take it a step further here. What we're going to see is there's actually really nice formulas that result from this because of the connection with trig. And we have those trig identities that are able to condense stuff down. So before we give the formula for multiplying complex numbers, I actually want to build through that, okay? So let's go ahead and try an example of this. We are going to take the complex number 3/2 plus 3 root 3 over 2i, and we are going to times that by 2i, okay? So I definitely can go through, and this is not one that's bad for me to multiply out because I only have a single term here, so I can distribute it to each piece. So if I take 3/2 and times it by 2, that leaves us with 3i. And then I have 3 root 3 over 2 times 2. That would leave us with 3 root 3. And then the I times I gives us I squared. So I need this complex number to be in standard form. I squared is -1. So this part really turns into the real part. This becomes -3 root 3. And then we put the imaginary part second. So again, this one, not hard to do with actual multiplication. But now what I want to do is actually utilize the trig form and see if I get something that happens that I can maybe generalize from there, okay? So I'm going to go ahead and I'm going to find the trig form for each of these numbers. Okay, so if I start with this first one, 3/2 plus 3 root 3 over 2i, that is going to be in quadrant 1 because both x and y are positive. So my x value is 3/2. My y value is 3 root 3 over 2. And then to find r, we take each of these squared. And that's equal to r squared. 3/2 squared would be 9/4. 3 root 3 squared gives you 9 times 3. So that's 27 over 4. And that's equal to r squared. They both have the same denominator. So 9 plus 27 is going to be 36 over 4 is r squared. 36 divided by 4 is 9. And so r is going to equal 3. And then again, you can utilize tangent of theta. Your angle is just the one right here in quadrant 1. You can also go ahead and pick off cosine of theta is adjacent over my hypotenuse. So that is going to be 1/2. And then sine of theta is the opposite side over the hypotenuse. So that leaves us with root 3 over 2. So for cosine to be 1/2 and sine to be root 3 over 2, our theta value has to be 60 degrees. And so I'm going to utilize numbers because again, going to be a little bit easier just to build this equation. So this number in complex form is going to be 3 cis 60 degrees, okay? My second number, way easier to actually go through because it has no real component, so it is just on the y-axis. So that one is really nice. So if I look at 2i, I want to give myself some room because we can really do this pretty simply. If I look at 2i, my imaginary component is 2. So from this, our theta value is going to be 90 degrees, and our r value is just the distance out to that point. So 2i in complex form is going to be 2 cis 90 degrees, okay? So if I want to multiply these two, that is really exactly the same as multiplying 3 cis 60 degrees times 2 cis 90 degrees. Okay. Well, I'm going to multiply the like things. So we can multiply the 3 and the 2. So that's going to leave us with a 6 out front. And I'm definitely going to need some room. So I'm going to put my equal sign way over here. Then I'm going to have to multiply cis of 60 degrees plus cis of 90 degrees. So I'm going to full write those out. Cis of 60 degrees is cosine of 60 plus I sine of 60. And then cis of 90 is cosine of 90 degrees plus I sine of 90 degrees. Okay. And if I want to multiply these two out, unfortunately, I am going to have to FOIL this thing. So we got a lot to FOIL. We go ahead and multiply our first terms. So that would give us cosine of 60 degrees, cosine of 90 degrees. Okay. Then we go through and we multiply the outer. So that would be 60 and I sine of 90. So to make that convenient, I'm going to put the I out front. Cosine of 60 degrees, sine of 90 degrees. Then we do our inner. And again, just putting that in order, we'll put the I out front. I'll do the cosine first. That's cosine of 90, sine of 60. Okay. And then our last, I lost my 9 in there. We get I times I, so that gives us I squared sine of 90, sine of 90. Okay. So maybe you see something that happens in here, but you have cosine, cosine, sine, sine. That I squared is going to turn into a real number. So this is going to be one of our sum formulas, or our product of sum formulas. And then these both deal with an I, so I can factor that out. And then I'm going to be able to condense that because that's another sum and difference formula. So just rearranging those like pieces. We've got this and this that are alike. So that's cosine of 60 degrees, cosine of 90 degrees. And then I squared turns to a -1. So we get minus sine of 90, sine of 60, sine of 90. When I dropped my number, I thought it was a 9, but that really should be a 6 there. Problem with erasing things. So this is sine of 60, sine of 90. Okay. Then looking at this next piece, they both have an I in it, so I'm going to go ahead and factor that out. And that leaves us with cosine of 60, sine of 90, plus cosine of 90, sine of 60. So you can rearrange that to see you get the opposite for each variable. Okay. And now using our sum and difference formula, this condenses to cosine because it's the same on each side. And we add those angles because it's the opposite sign. So this would be cosine of 60 degrees plus 90 degrees. And then for the second piece, we have I. We've got the opposite of each value. And then it keeps the same sign because this condenses to sine. And then we go ahead and we add those angles together. Okay. So this ends up resulting in 6 cosine of 150 degrees plus I sine of 150 degrees, or really 6 cis 150 degrees. And then to show you, you indeed do end up with exactly the same thing we got way back up here. You can take cosine of 150 degrees. That ends up being in quadrant 2. It is a 30-degree reference angle. So cosine of 150 is negative root 3 over 2. And then sine of 150 is positive 1/2. So you get 1/2 I. Then distributing the 6 divided by 2 gives you 3. And then same thing over here, you get 3. Okay. So this seems like a lot of work in comparison to the fact that that multiplication was very easy to do. But the beauty of this is if you have really complicated numbers, or say we're multiplying 3 or 4 of them, you can instead look at that trig form, and all you do is multiply your two R values. Here, those R values were 3 and 2, and then you just add the angles together. So this is exactly our product theorem, and then it also corresponds to our quotient theorem, because that one is very, very similar. So if I take one polar form, or one trig form, where I have R1 cis theta 1, and I want to times that by something R2 cis theta 2, we just go ahead and we multiply the two R values together, and then we add the angles. Okay. If I'm dividing and I have them in those complex forms, you just go ahead and you divide the R values, and then instead of adding the angles, you just subtract them. Okay. So this is really fantastic when we have messy numbers and messy trig numbers, or they're already in trig form. Instead of having to expand that out, we can just go ahead and we can use the simplified process. Okay. So let's try an example. We're going to write the number in complex form, and I'm going to do it where it's already given in trig form, because these are not angles that we'd be able to spot on our unit circle. So if I want to go through and I want to divide these two, I'm not going to put them in complex form to start with. I'm going to utilize that they're in trig form. We go ahead and we divide these R values, and then we go and we subtract those angles. So 4 over 28 does simplify. They're both divisible by 4. So that leaves us with 1 over 7. And then 160 minus 40 leaves us with 120. So this is equal to 1 over 7. And then we get cosine of 120 degrees plus 1 over 7I sine of 120 degrees. And then that's an angle we know, a 60-degree reference angle in quadrant 2. Means cosine of 120 is negative 1/2. And then sine of 120 would be positive root 3 over 2. Because again, that is up here. So cosine's negative, sine is positive. So multiplying that out gives us negative 1 over 14. And then we get root 3 over 14i. So that is our number in trig form, or in complex form. Okay. So going back up here, instead of going again through all of this, it would have been much easier. We just multiply the two pieces. Then that leaves us with cis of 60 degrees plus 90 degrees. And so we get 6 cis of 150 degrees. Okay. And then we just figure out what cosine of 150 and sine of 150 is. So we did this just to prove that formula and show where it comes from. But again, it makes life much easier when you have complicated stuff, or if you're given angles that don't have a very nice complex form, because 160 degrees would not have nice outputs for cosine and sine. Same thing with 40 degrees. So in the end, we were able to get clean coordinates. Okay. Now, if we want to go through and we want to deal with complex powers, so that means taking something to a power, it's really just going to stem from the product theorem. Okay? So if I want to take a trig value and I want to square it, all that means is we're taking one trig value and timesing it by itself. So applying our product theorem, you multiply the R values and then you add the angles. But when you add the same angle twice, it just results in 2 theta. Okay. So what happens is the power distributes to R and you multiply theta by that. And then in the exact same way, if you wanted to take R cis theta and raise it to the third, well, all you're going to do is you're going to raise the R value to the third, and then you'd have cis theta times cis theta times cis theta. You'd add all of those angles together. So we get cis of 3 theta. Okay. So this is something that's called de Moivre's theorem. It's just a mathematician. But if you want to take a complex number in trig form and raise it to the nth power, you raise your R value to that and you multiply your angle by that. Okay. So let's try an example of this. Let's go ahead and we're going to find the given power in its rectangular form. Okay. So what this really is saying is we're taking 2 cis 90 degrees and we're raising this to the 6th power. So applying de Moivre's theorem, that gives us 2 to the 6th. And then we have cis of 6 times 90 degrees. Okay. So 2 to the 6th is going to be 64. And then we're really finding cis of 540 degrees. Okay. So really that's 64 cosine of 540 degrees plus 64i sine of 540 degrees. Okay. And if you think about that, it's divisible by 90, so it's a multiple of 90. It's a matter of where that falls on the unit circle. So this would be 360 because it's definitely bigger than that. Add 90 to that gives you 450. Then add another 90 to that. It's going to give us 540. Okay. And so that happens to be exactly where our angle is. It's a multiple of 90, but it lands on the negative side of the x-axis. So cosine of that angle is going to be -1, and sine of that angle is 0. So it ends up being that when I take this complex number and I raise it to the 6th power, because initially I sine of 90 means you have a purely imaginary number, it gives you something that is real, okay? But this would be so tedious to do otherwise. So this is a really nice theorem that helps us out. The main application of this, though, is dealing with roots. So this is something that's definitely a bit more complicated. So I've saved most of my examples for this. But the idea is, if you remember back in pre-calc or even back in college algebra, when we were talking about finding roots or zeros of equations, if you have a fifth degree polynomial, it has 5 zeros. It might be that you have repeated, or you can also have those complex solutions. So we're going to start out by talking about the roots of complex numbers. So if you think about a number, you can take however many roots you want, but the same idea is going to hold for complex numbers. You can take a fifth root of 32, you can take a fifth root of 70. Might not be a nice number, but you can definitely take it. So the same idea is going to hold here. If I have a complex number, it has n distinct complex nth roots, okay? So here, the complex number a plus bi is an nth root of a different complex number if, when I take this complex number and raise it to the nth power, it lands me at my original complex number, okay? So that's the idea. We're taking the nth root of this side and we're landing on a. The distinction is here, when I take the fifth root of 32, it's 2. So that's the real root. However, if I take the fifth complex root of 32, there are going to be 5 different complex roots. And the reason is because of this unit circle. So if the point is right here, again, as long as I land at that point as well, I still am at the same spot. So because there's this connection with the unit circle, I'm able to actually see more roots than there were before, okay? So let's start with an example. Let's find the cube roots of 8 cosine of 135 plus I sine of 135. Okay. So the idea is here, if I have a number, r cis theta, if this is a cube root, of the number that's given 8 cis 135 degrees, then if I take this number and I raise it to the third power, it's going to equal 8 cis 135 degrees, okay? So again, this way, if I take a cube root of each side, it gives me r cis theta. But it's much easier to work with the powers to start with. Well, applying our de Moivre's theorem here, that's really r cubed cis 3 theta. And then over here, we've got 8 cis 135 degrees, okay? So kind of matching these up, we're able to see some things. We've got r cubed better equal 8, so that's fantastic. And then we're gonna work with 3 theta equaling 135. But the problem with this, remember, is it doesn't necessarily just need to be 135. Because as long as I land in that same spot on the unit circle, I'm gonna get the same output for cosine and sine. So 135 is right in here with a 45-degree reference angle. Really, if I go once more around the unit circle, I'm still going to get the exact same output for these two values, and it gives me exactly the same complex number. So there is a connection with these, but it's really going to result in solving a trig equation, okay? The r is not terrible to deal with, though. So comparing the pieces, r cubed definitely needs to equal 8, and r is a positive real number, so r is equal to 2. No problems with that, okay? The problem is if it's a cube root, I need to find 3 cube roots. So it's going to deal with 3 theta equaling 135 degrees. Okay. The other issue, though, is, again, remember that 3 inside the cosine and sine function ultimately affects the period and how fast you go through one revolution of a unit circle. Our angles we want to be between 0 and 360 degrees, just for simplicity. But there's actually going to be a few times between 0 and 360 that we land here because of that 3 theta impacting the period. So 3 theta needs to equal 135 or any angle coterminal with 135 degrees. Okay. So remember when we had to find all of the values within the interval from 0 to 2 pi or 0 to 360 degrees, we'd have to add one revolution of our unit circle to be able to see if that fit into that time period. So 3 theta could definitely equal 135, and that will be one solution. Or it could equal 135 plus one revolution around the unit circle, because that still lands me in the same spot as 135. Or 2 revolutions, or 3 revolutions. Okay, or really as many as you want to from there. Okay. The idea is, though, I'm looking for cube roots. There's really going to be 3 of them, so I only need to deal with the first 3 in this instance. But just to show you, so 3 theta can equal 135 degrees. If I go once around the unit circle, that angle that's coterminal with 135 would be 495. So again, that means we went around once, and then we stopped right here at that 45 degree angle. If I go around twice, so that would be adding 720, that lands me at 855 degrees. And again, that means we went around once, we went around twice, and then we landed at the 35 degree spot. And then if I add 3 times 360, that lands me at 1,215. And again, I can keep going from there. All of those angles will still be coterminal with 135. But now I just want to get theta, so I'm going to go ahead and I'm going to divide everything by 3. So that leaves me with theta. 135 divided by 3 is 45 degrees. 495 divided by 3 is 165. 855 divided by 3 will land us at 285. And then 1,215 divided by 3 is 405. And then that list keeps going. Okay. So again, I'm really only looking for the angles between 0 and 360 degrees because that's what our angle we said should be to just avoid confusions. So these are all of the ones that will give us the same output for cosine of 3 theta and sine of 3 theta landing at the same spot as 135 degrees. So these are the 3 angles we're going to use for the 3 roots. This one went a little bit further. It's actually coterminal with 45 degrees. Okay. So we have 3 cube roots. Of the number 8 cis 135 degrees. The first one is going to be 2 cis 45 degrees. The second one is going to be 2 cis 165 degrees. And the third one is going to be 2 cis 285 degrees. Okay. So again, the way that you'd be able to check this is if you took 2 cis of 45 degrees and raised it to the third power, it better result in the exact same complex number as the one we started with, which is 8 cis 135. And then same thing here, if I took 2 cis 165 degrees and cubed it, it would result in exactly the same as 8 cis of 135. The angle inside would look different, but it still will have the same exact input or output for the cosine and sine function. Because if you do 165 times 3, let's see, what is that? That would be 495, and 495 is coterminal with 135 degrees. So same exact output for sine and cosine. And likewise, you can go through and you can check if you take 2 cis of 285 degrees, raise it to the third power, it results in the exact same complex number as 8 cis 135. Okay? So this is what we call our nth root theorem. The complex number r cis theta has exactly n distinct roots, nth roots, given by the following. You take the nth root of the value of r, and then we have cis of some angle, where this angle alpha on the inside is going to be that theta value, plus however many revolutions around the unit circle, divided by the number of roots. And so that's exactly what we did here. We took theta, we added 1 revolution, 2 revolution, 3 revolution, and then we divided it by 3. Okay. So this value of k starts at 0, and you go up to 1 less than n. Okay. So again, going back up to this example, we added no revolutions, 1 revolution, 2 revolution, and that was the cutoff. Okay. We only needed to do 2 revolutions to be able to find all 3 roots, because you start with 1 at 0 revolutions. Okay. So let's do some more examples of this. We're going to find all of the 4th roots of 81i. So the first thing I want to do is I want to put this in trig form. Because it's much easier to find the roots in trig form. Okay. And 81i, thankfully, is much nicer because it is just imaginary. That distance out is 81. That angle is 90 degrees. So 81i is equivalent to 81 cis 90 degrees. Okay. So all of our 4th roots have the same r value. Which is the 4th root of 81, which is just 3. Okay. Now I need to find the 4 angles. So utilizing that formula, the angles start with 90 degrees. We add 1 revolution around the unit circle, times it by however many revolutions. And we keep doing that process. And then we divide by 4. So you really don't need to memorize this particular formula. Instead, I think the easier way to think about it is you start at 90 degrees divided by 4. Then you find the next coterminal angle, which is where you add 360 degrees, divide by 4. The next coterminal angle is 2 revolutions. And that's 3 angles now. And then we have 1 more. So with this, we have 1, 2, 3, 4 angles. And at that point, I'm going to trust that you can definitely add these, multiply. 90 divided by 4 is 22.5 degrees. 90 plus 360 over 4 is 112.5. Then we're going to get 202.5 degrees. And finally, 292.5 degrees. So the fourth roots are the following. We've got 3 cis, the first angle, 22.5 degrees. We've got 3 cis, 112.5 degrees. 3 cis, 202.5 degrees. And 3 cis, 292.5 degrees. Okay? So I just have one last example to kind of tie all of this in together. We want to find all the complex solutions of x to the 5th minus 1 equals 0. So you have found real solutions of this, and realistically there is only one. So what we want to do here is we want to see there should be 5 distinct solutions, and they are all going to actually be complex. So if you were to solve this normally, x to the 5th minusing 1 equals 0, you add 1 to the other side, x to the 5th equals 1, and then you technically get 5 solutions. It's the 5th root of 1. So this only results in giving us a single solution of 1 that's real. So what we need to do is we really need to find the complex roots. And specifically the complex 5th roots of 1. Okay. So if you think about writing that in its trig form, well, it just has a real component. So positive 1 would be right here. The distance out to that is 1. So that angle is 0 degrees. So this is really 1 cis 0 degrees. Okay. So our value of r would be the 5th root of 1, which is 1. And then our alpha, we're going to have 5 different angles. The starting angle is 0. The second angle is 0 plus 360, so 1 revolution. Next angle is 0 plus 2 revolutions, which is 720. Then 0 plus 3 revolutions, that's 1080. And that gives us 1, 2, 3, 4. So I have to do this one more time. So 0 degrees, and adding 1 more 360 would give us 1440. And then I want to take all of these and I want to divide it by 5. So this gives me the 5 angles for that trig form of those solutions. So if you do the addition and division, the first angle is still 0 degrees. Second angle is 72, then 144, then 216, and then after that 288. Okay, so we have 5 angles corresponding to the 5 solutions, and they are all in trig form. So it is r cis the first angle, then r cis the second angle, r cis the third, the same with the fourth, and finally the last angle. Okay, so these are all 5 solutions of x to the 5th equals 1. And again, in the real plane, there is only a single solution, 1. However, there are really 5 that result from this. So that would give us 5 unique complex numbers that raised to the 5th power all result in 1. Okay. So again, this is just a nice connection to some stuff we've done before. Working with polar is a lot easier than working with some of our complex stuff, which is a big benefit of this.